To chapter 4, and this would be obviously a start of exam 2 material. So in chapter 4 here, we're going to talk about atoms. We're talking about some experiments that led to the understanding of the structure of atoms. We'll also talk about atomic number, mass number, and some other properties of atoms. So but first, we're talking a little bit about compounds. We talked and touched upon compounds in an earlier chapter, but just a reminder that, you know, the difference between a compound and a molecule is really a molecule is just a basic definition of two or more atoms that come together. With a molecule, that could be the same elements, or they could be different elements. But when we do talk about a compound, it does need to be different elements. So they need to be atoms that come together of different elements. So for example, water obviously has hydrogen and oxygen. It is a compound. It is also a molecule. And as we talked about earlier on as well, again, it would not be an element because obviously it's made up of different elements that are there. Now, when we write chemical formulas, we do use the symbols for each of the elements, and we do write next to the symbols a subscript. So for like H2O, the subscript always goes for the element that is to the left of it. And in chemistry, if there is nothing written, it is assumed to be 1. So typically we don't write 1 in formulas or really anything. But we do look at those subscripts to the left of them. Those represent how many atoms of each of those elements are present. It also represents, as we'll talk about later on in a different chapter, how many moles of each of those guys are present. That also goes if we had some type of formula like this. The 2 here would go for the aluminum, so there'd be 2 atoms of aluminum. In this case, we would distribute the 3 in, so there would be 3 atoms of sulfur, and then we would also need to multiply the 3 by the 4 there, and there would be 12 atoms of oxygen. So 12 oxygens, 3 sulfurs, and 2 aluminums in this formula. So if you do have something like that that does have parentheses, which happens a lot, those are what are referred to as polyatomic ions, and it does have a number on the outside. You do need to kind of distribute that in there. So some other examples of compounds here, once again, carbon dioxide, 1 carbon, 2 oxygens, 1 nitrogen here in ammonia, and 3 hydrogens are present. So if we look at some of these examples here, a molecule that contains, 6 carbon atoms and 6 hydrogen atoms, we would write the formula C6H6. The dashes are just from PowerPoint. They're not any part of the formula. If we have a compound that contains half as many calcium atoms as chlorine, so obviously we have 2 chlorines, half of 2 would be 1, so we don't write the 1. Would give us calcium chloride in terms of its proper formula. And lastly here, sodium nitrate. So we have the equal number of sodium and nitrogen, but 3 times as many oxygens. So we basically, again, have 3 oxygens, 1 nitrogen, and 1 sodium here. That is how we do write chemical formulas using the symbols. And again, those subscripts, we never use big numbers, you know, or anything like that. And the formula is always sort of what is here. In an equation, we will sometimes put a coefficient in front, which also sort of distributes how many of each of those sort of units we have. But when we talk about just the chemical formula, it is those subscripts that you should have. Obviously, if you ever change the subscripts, you wouldn't change what it is. So we typically do not change the subscripts unless we are kind of changing what it is. Now, when we talk about atoms, atoms are basically made up of 3 parts. There's the protons, electrons, and neutrons that are present. So we're going to talk a little bit about some of the experiments along the way here that really led to a much better understanding of basically the structure of the atom. So as we go through it, I'll kind of tell you what you do need to know, and so we'll talk about that. So whoops, come in. So really, it all started a long time ago with really this understanding of matter is composed of these really small, indivisible particles, which early sort of philosophers named atomos, which is sort of a forerunner, obviously, to atoms. And then obviously, as sort of technology advanced and people started doing experiments to sort of study the structure or the nature of atoms, sort of our understanding of the atom sort of evolved. And a couple of things were sort of believed here early on, that most materials are mixtures of pure substances. Remember, a pure substance is just something that is by itself, not combined with anything else. Obviously, mixtures is when you start combining a couple of pure substances together. Pure substances are either elements or compounds. And the idea of the law of composition is a given compound will always be made up of the same composition regardless of where it comes from. So when we take something like water, it's always 8 grams of oxygen for every 1 gram of hydrogen. And that's because there's H2O, so there's always 2 hydrogen atoms for every 1 oxygen atom that's present. And hydrogen's about 1.008, oxygen's about 16 grams. So if you got about 2 of them, you got about 2 grams to 16, and that's basically if you divide it 1 gram for every 8 grams of oxygen. So that's basically how they get to the 8 grams of oxygen for every 1 gram of hydrogen that is present. And no matter where you get your water, how it's bottled, just the water component should again always be 2 hydrogens and 1 oxygen. Sort of that 8 grams to 1 gram relationship should always be there. Now, sort of an early understanding or idea of the atom came with Dalton's atomic theory. It is not correct, sort of overall in a couple of parts of it. Some parts are correct. So as we talked about earlier on, a theory is sort of something that can be sort of readjusted, maybe reevaluated, maybe thought of as not being correct in all aspects. Once further sort of experimentation happens. So that's John Dalton there. He sort of good understanding of math and sciences. He took down the weather every day. He never married, surprisingly, but he did like to go bowling on Thursdays, which of course, if you learn nothing in this class, that is definitely what you should know, right? That he went bowling on Thursdays, not Tuesdays. Not discount Fridays, but it was Thursday. Probably every test from now on. Yes, it will be. Was not very good public speaker, but he was a good lecturer. But really what we sort of think about Dalton, other than bowling on Thursdays, was that he came up with sort of a precise definition of what we sort of call atoms. So let's take a look at some of Dalton's atomic theory here. And these are some of the parts. And we're going to talk about some of the things that are maybe not so true as well. So he felt that elements are composed of extremely small particles called atoms. All atoms of a given element are identical, having the same size, the mass, and chemical properties. Atoms of one element are different from atoms of another. He felt compounds were composed of atoms of more than one element. A chemical reaction really involves only the rearranging of these atoms. So basically breaking bonds, rearranging on new sort of substances on the other side. We don't create nor destroy anything. And that's the idea as well of the law of conservation of mass. Because really we're only sort of breaking apart bonds in a chemical reaction, we do not lose any elements, which means if we had 6 carbons on our reactant side, we should end up with 6 carbons on our product side. They may be in different sort of compounds and stuff on the product side, but because 6 carbons weigh 12 grams each, you got about 6 times 12 on the left, and you got about 6 times 12 in terms of the mass on the right. And, you know, you will have the same 72 grams there of carbon basically represented on each side. That's also why when we get to equations, as you might know, and as we will talk about, obviously, when we get there, we always want to balance an equation. So we should never lose any elements along the way or anything like that. So a couple of things about Dalton's atomic theory, which you should know these main points of it, that were found sort of later on not to be sort of true, if you will, whereas the idea of all atoms of a given element are identical. So the existence of isotopes, as we'll talk about in this chapter, isotopes are the same element, but they have different masses. So clearly, if they're the same element, but they have different masses, they are not identical to each other. So the existence of isotopes sort of disproved that. Also, the idea that Dalton had as well, that atoms are sort of indestructible in a chemical reaction, that's true. And things like a nuclear reaction, we do actually change the elements from one element to another. So those are kind of the couple of points where Dalton's atomic theory are not so correct. But atoms of different elements are different from each other, and compounds are composed of more than one element is still true. And the idea that chemical reactions just involve sort of rearranging of those atoms also true as well. So the idea of indestructible and the idea that all elements have the exact identical atoms are not true anymore. Any questions on up there? So here's the idea that Dalton pictured compounds. It's really a collection of atoms. And, you know, we talked a little bit about elements. And again, elements are really your basic building blocks of everything. So the idea here is obviously, if elements are kind of like the letters in the alphabet, you can make many, many different words, depending on the combination of letters that you use. Same idea here, different combinations of elements, and even really different amounts and combinations of the same elements will give you different compounds. So the properties of all three of these guys, even though they are all basically the same two elements of nitrogen and oxygen, they all have different properties depending on, you know, the amount of oxygen is there, the amount of nitrogen is there, how they're bound together. So even really compounds that share true similarity in terms of the elements that are present can have different properties, you know, based on the arrangement that we have there as well. So let's talk a little bit about the structure of the atom. So based on Dalton's atomic theory, there was this sort of idea of an atom is really the basic unit of all elements that can enter into chemical combination. A lot of experiments were done since that time. And even though atoms are extremely small, they sort of revealed the idea that they do have an internal structure. So even though they are really, really small, they do contain what are sometimes referred to as subatomic particles. And investigations led to the discovery really of three types of subatomic particles. Those are electrons, protons, and neutrons. As we will talk about, electrons are negatively charged. Protons are positively charged. And neutrons, as we will talk about, have no charge. And really, because these sort of subatomic particles contain charge or do not contain charge, that really sort of allowed different types of experiments to occur. And really, one of the basic principles of sort of chemistry and how a lot of things sort of interact with each other is the idea of opposites attract. So once again, anything that is positive will be attracted to anything that is negative. And things that have the same sort of charge will repel each other. So anything that's positive and positive do not like to be around each other, or anything that is negative and negative also do not like to be around each other. So this idea of opposites attract was really useful in a lot of these sort of experiments that were done to understand these different types of particles and maybe where they are located within the atom. Any questions on that there? So we're going to first start talking about the electron and some of the experiments that helped us understand the electron, and really a lot of experiments that it led us to really understanding the electron involved what's referred to as the CRT, and that is the cathode ray tube. And a cathode ray tube, sort of a diagram of it here is on the bottom. It's really a tube that shoots negatively charged particles. And there is a sort of electrical field, the positive plate on one side, negative plate on the other. So these negatively charged particles are attracted to the positive side of the plate and are obviously want to move away from the negatively side of the plate. Sometimes they'll put a fluorescent material here so they can kind of see where the beam actually hits. So when we talk about these other opposites attract, we can really also think about sort of electrical fields, and to the same sort of effect, magnetic fields are oftentimes used in a lot of these experiments to sort of take advantage of the charges. So if I have, say, an electrical field and I shot a particle and it kind of tilted upwards towards the positive field, that particle should be positive, negative, have no charge. Opposites attract, so that little beam there would have a negative charge as it bent towards the positive guy. Same thing if I shot a particle and it sort of leaned towards the negative side, we would know that that guy is most likely going to be a positive particle. And lastly, if we shot one and it really just went kind of straight through, it would have no charge, right? So it wouldn't be affected. So anything where we kind of use something like a magnetic field or electrical field, a magnetic field as well, which has a positive pole and then a south pole, north pole, which kind of works the same way. We could use that sort of advantages to help us understand what's going on here. This is also years ago. Although you guys probably, maybe there's still one laying around. Older TVs used to have cathode ray tubes in it. They used to be like the picture tubes, like the really old ones used to be on the ground, you know, open up the back, you fix them, you know, before you just went to Costco and buy a new one, right? So they have TV repairman and stuff like that. But old sort of TVs that had like big backs had cathode ray tubes. Old computer monitors, not like this one, but also had like the big kind of back that comes out of it. Those were also CRT monitors as well. So like I said, they would shoot an electrical beam that's negatively charged. Again, they use some type of fluorescent material. You can kind of see the beam. Here again, our north and south pole in our electrical field. Neutral beam going straight through. Again, somebody tilting up towards the negative or north pole there would be positively charged. Somebody coming down to the positive or sort of south pole would be negatively charged. And that is a picture of a cathode ray tube. And again, when this is turned on, you'll be able to see kind of the little dots and stuff like that. I don't think I have it here to play it, but I'll see if I can find it maybe next time. So one of the earliest experiments that were done to help us sort of understand the electron was done by Thompson. And Thompson used the cathode ray tube. And there he is with his cathode ray tube in front of him. And basically what he was able to discover was the charge to mass of an electron. So he's able to determine what the charge to mass ratio of an electron was. So the first really main understanding of an electron was done by Thompson. He used the CRT tubes there and basically was able to figure out the charge to mass of an electron. And that ratio was minus 1.76 times 10 to the 8 C, which is a coulomb, and that's a unit of electrical charge per gram. So charge to mass of an electron. And this was a good understanding of our electron, and sort of further understanding of the electron came with another really important sort of experiment And this was one that was done by a guy named Milligan. And Milligan did what is sometimes referred to as the oil drop experiment. So let's take a look at that here. So Milligan did this oil drop experiment. And basically what he did is he had this chamber and he had sort of an electrical field. And much like the name implies, he shot some oil droplets in. And the oil droplets are going to want to drop based on gravity. And what he was able to actually do was he was able to really adjust the electrical field in that sort of chamber in such a way that basically the oil droplet just kind of hung there, basically. So it wouldn't drop, obviously, when it go up. He was able to get basically the oil droplets to just hang there as it gained a charge coming down, and using the advantage of that charge and the electrical field, he was able to do that. And what he was able to determine was the charge of an electron. So Milligan did an oil drop experiment. He was able to determine the charge of an electron. So these two experiments are really important together. We have Thompson, who used the CRT tube to figure out the charge to mass of an electron. And we had Milligan here, who was able to determine the charge on an electron. So if I know the charge to mass of an electron and I know the charge of an electron, we actually could use both of those values together and do a little math here. And from those two experiments, you're able to put it together and really determine the mass of an electron by the two results of those experiments, taking the charge and really dividing it by the charge to mass of an electron that was determined by Thompson. So Thompson CRT tube, charge to mass, Milligan doing this oil drop experiment where he was able to really suspend the oil droplet using the charge that it gained and the electrical field. And again, putting both of those values together allows us to actually calculate the mass of an electron, and this is the mass of an electron in grams. It is 9.09 times 10 to the minus 28 grams. Is that a large number or a small number? That's a really small number, right? Just like 27 places to the left and put a bunch of zeros, right? Any questions on that? So again, two important things to understand about the understanding of the electron. Thomson's experiment, Milligan's experiment, what came out of both of those experiments, and obviously how the results allow us to determine the mass of an electron. So these experiments let us understand that obviously an electron has a negative charge. We also now have the mass of an electron. So what this allowed people to do sort of at this time was to sort of formulate an idea of what they believed the atom was looking like at this point. So one of the main ideas that they sort of understood at this point was the atom is basically electrically neutral. So obviously through these experiments, they were able to determine that the atom does contain these negatively charged electrons and that they were electrically neutral. So in order for something to be neutral, if it has something that is negatively charged, the atom must have something else that is positively charged to balance it out. So there's always this understanding that although it does contain electrons, there has to be something else in the atom to balance out the negative charge from those electrons. And sort of the early model of the atom was the one that was proposed by Thompson. And Thompson proposed what is sometimes referred to as the Plum Pudding model of the atom. And the Plum Pudding model of the atom is essentially this sphere of positive charge. So you got this sphere of positive charge. And embedded inside the sphere of positive charge are these negatively charged electrons. So we have this really big sphere where the positive charge is really spread out all over it. We have these electrons sort of embedded inside. Plum pudding is like a rice dessert with raisins embedded inside. So the idea there, raisins kind of like the electrons. the rice is sort of spread out, is over the whole thing. So the idea here is we have this really fast positive charge with these electrons inside. Here's a much nicer picture of it. And this was sort of a accepted model until basically some more research and more experiments were performed. And the next really major step to the understanding of the atom really came through the gold foil experiment. So the gold foil experiment was one that was done by Rutherford and some other guys like Geiger and Marston. And what they used was gold pieces of foil, and they shot alpha particles at it. So there's three sort of radioactive particles that were commonly used in a lot of experiments. There were alpha particles, which are basically positively charged radioactive particles. They're basically helium. There were beta particles, which were basically electrons, so they're negatively charged sort of particles. And in terms of the third sort of radioactive particle or ray that is oftentimes used, were gamma rays. And gamma rays sometimes has this abbreviation, basically has no charge. So really these three sort of radioactive particles were used a lot of experiments. They sort of mimicked the really three subatomic particles. You got something that's positively charged, you got something that is negatively charged, and you really have something that is no charge. So what Rutherford used was alpha particles. So he used these heavy radioactive positively charged particles, and he basically shot it at pieces of gold foil. Now, what he expected to happen and what actually happened were really a couple of different things. So if we think about sort of the early model of the atom that we just saw there on the previous page, what he expected to happen was when he shot these alpha particles, because they are heavy, because they're moving fast, and they are positively charged, he expected really these particles to come through, but sort of have some deflection. So if you think about sort of if this non-circle here was our atom, and all of our positive charge was really just spread out over the entire thing. And if somebody held one side of it and I held the other, and we shot this pin at it really fast, right? It probably would bounce through, right? And cut through with a little bit of deflection as it went through. And that's exactly what they sort of expected to happen. They expected it to go through, but with a little bit of deflection as we are shooting sort of positive at positive. What they actually found happened when they shot it up, and they have this sort of deal. They have a source of our alpha particles here. We have a deflection sort of screen. What they found was most of the particles went right through pretty much straight with no problem. So they shot these alpha particles, went right through the piece of gold. Obviously the gold, it has a bunch of gold atoms in it. So they're shooting it really at the atoms of gold. And most of the alpha particles just seemed right through, no problem, no deflection. What they did notice was every so often, they would get these alpha particles sort of scatter at really large angles. And sometimes they would even kind of head back to where it was shot at, which is not really, really good. And you can see that here on the screen, some of them reflecting out at some of these larger angles, not going straight through. So this was really surprising for Rutherford to see that most of them went through undeflected, but every so often we did get these guys to bounce off at these really large angles. So kind of compared it to if you shot a gun at a piece of paper and the bullet comes back to you, not really what you're expecting to sort of happen in those type of cases. In order to make these heavy, fast-moving, positively charged alpha particles to scatter at really large angles, what did it have to hit? It had to hit something that was what type of charge? Positive, really, really densely positive charge, right? To make it sort of bounce over. So if we thought about sort of our atom as the positive charge really spread out, if we instead took all of our positive charge and we folded it, what do they say, 7 times you could fold a piece of paper without being able to fold it anymore. But if we really concentrated all of our positive charge in here and then shot, that was a really bad throw. What's that back? Thank you. I know. Thank you. What? I know. I'm going to try it with the bigger shot here. There we go. All right. Well, this is a bad piece of paper. But if we really concentrated the positive charge, what's going to happen when we shoot it with those positively charged particles is it's obviously going to hit it and bounce off. I don't know, it works much better with a full-size paper. I know. I went with a scrap paper. I didn't want to ruin that paper. So what happened as a result of this is they really had to sort of rethink the model of the atom that was there. So basically what they said was, this is really not what we observed. This over here is really what we saw. You know, most of them sell through, no problem. So they had to sort of explain this. And what they came up with is really sort of the modern version of the atom. What explained basically all those guys that went through with no problem was they really didn't run into anything that had a charge. So they basically ran into empty space. So they felt that most of the atom was empty space, which accounted for why most of the particles, like I said, went through no problem, didn't have any situation where they bounced off. What they also found was all that positive charge had to be in a dense core, which they called a nucleus. And that accounted for why we saw these positively charged alpha particles shooting off at really large angles. And the idea was, as you can see here, electrons are really in that empty space and they are moving around. By the way, as we will talk about, electrons are out from the nucleus at some point, but they are moving around randomly about the atom. They do not move in pretty circles or anything like that. They do move in a very random sort of fashion around the nucleus in that empty space. Do we anticipate that there would be attraction between electrons and the nucleus? The answer is yes. Since the nucleus is really positively charged, electrons are negatively charged. There is going to be attraction between the two, but they again do not move around in those pretty circles. So they do move really, really randomly about it. So here's sort of a table summarizing some of the important experiments that we talked about in our understanding of the atom. Again, sort of gas discharge tubes were sort of the forerunners to the CRT tubes. Really the first set of experiments using the CRT tubes, again, was Thomson and Milligan, allowing us to understand really the mass of an electron from those two, along with Rutherford's gold foil experiment, which basically turned the page on the Plum Pudding model to our modern sort of version of the atom, mostly empty space. The nucleus that has a positive core. And one other major difference between the Plum Pudding model and the sort of current model is in the Plum Pudding model, they felt that most of the mass of the atom was actually the electrons. In the modern version of the atom, most of the mass of the atom is actually the nucleus. So once again, that also is something that's a different sort of version. Again, in the earlier model, most of the mass they felt was the electrons, but with this sort of new model, they feel most of the mass is made up of the nucleus. Any questions on that there? So the idea of this positively charged particles, they basically felt that within the nucleus, they call those positively charged particles protons. Protons have a mass of 1.67252 times 10 to the minus 24 grams. And if you remember, the mass of an electron is 9.09 times 10 to the minus 28 grams. Which one's larger? Yeah, proton is about 1,840 times heavier than any electron. So that also basically helps us understand why they felt that the nucleus, which is where you find the protons, is most of the mass of the atom, because each proton is about 1,800 or so times heavier than any electron that there is. So electrons out from the nucleus flying around, negatively charged, positive protons within the nucleus. Each proton, again, 1,800 or so times heavier than an electron. So at this stage, they sort of thought of the atom. The atom is sort of like the Superdome, if you will, a really big stadium. And then kind of like the nucleus is a really small sort of marble or something on the kind of 50-yard line. So, you know, although atoms are really small, the nucleus is really, really a small part of it, but it does make up most of the mass of the atom. So there was always a thought that in addition to protons and in addition to electrons, there was one more sort of subatomic particle that was present, and that was the neutron. And it wasn't until about 1930 that Chadwick did a bunch of experiments, and he did a lot of experiments that basically resembled the use of X-rays, which is similar to gamma rays. And he discovered sort of the presence of that third particle, which is the neutrons. Neutrons have no charge, so no charge on our neutrons, also found in the nucleus. So in the nucleus, we have protons and neutrons. Protons being positively charged, neutrons having no charge. Again, out from the nucleus, we have our electrons. So protons, neutrons, and electrons basically flying around our nucleus. Now, the mass of a neutron was found to be 1.67495 times 10 to the minus 24 grams. That's why they go to so many decimal places. It actually slightly beats out the proton. So the neutron as well is about 1,840 times heavier than a electron. So if we think about what's inside our nucleus, we have both the proton and the neutron, and each of them are about 1,800 or so times heavier than any electron that's flying around. And that is why, again, Rutherford said that most of the mass of the atom is actually the nucleus, because they contain these really heavy particles. So in terms of mass, it is actually the neutron that is the heaviest, followed very closely by the proton. And then the least massive is actually the electron, which is much, much lower in mass. Any questions on that there? And as we can see there. So there's our three masses. Again, you do need to obviously know the experiments we talked about. So you need to know Dalton's atomic theory. You need to know Thompson's CRT experiment, Milligan's oil drop experiment. You need to know what the Plum Pudding model looked like and was about. You need to know Rutherford's gold foil experiment. And you need to know, obviously, the results of the gold foil experiment and how it sort of changed to our modern understanding of the atom, and obviously the modern understanding of the atom. Any questions on any of that there? So just to finish up here, protons, again, positively charged in the nucleus. Electrons negatively charged outside the nucleus. And neutrons have no charge, and it's in the nucleus. So, any questions on any of that stuff there? All right, we're going to lay that up for today.